after working with, they gave us the model, that's what we worked with on Friday. We said the model for an exponential function is y equals a times b to the x power. Where a cannot equal what? What can a be equal to? 0. What did we say about b? B cannot be equal to 1. And we want x to be, and we want b to also be greater than 0, right? Okay, so we already know what the exponential model is. Now what we're going to do today is first thing we're going to do is we're going to determine if they give us a set of ordered pairs with those points on a graph. If we graph them, would we get an exponential function or not? But we don't want to have to graph them. We just want to be able to tell some way algebraically, numerically, if it would represent an exponential function. So to determine if a set of ordered pairs represents an exponential function, here's what we're going to look for. If you have a constant change in x, then you can look for a constant ratio, not a constant change, a constant ratio in what? Remember, in other words, geometric sequences. Is there something that you multiply the previous term by to get your new term? So if we have a constant change in x, the x's are going up or down by the same amount. They're increasing by 1, they're going down by 2, whatever, that's an add and subtraction thing. If there's a constant change in x, then we're going to look for a constant ratio in y. So here's our first problem that we're going to do, and this actually comes from page 625. It's the check it out problem. Okay, 2a. Here's our set of ordered pairs. -1, 1, 0, 0, 1, 1, and 2, 4. We're going to check to see if that represents an exponential function. Well, the first thing we're going to do is we're going to put it in table form, so it's easier to look at. So we'll put our ordered pairs, and I made a horizontal table. You could make it vertical, it does not matter. 0, 0, 1, 1, 2, 4. It's just easier to look at now. We could just follow across the x's or follow down the x's if you make it vertical, and we can see, is there a constant change? In other words, are the x's going up or down by a constant amount? So are the x's changing by a constant? What are they doing?
Going up by 1.
They're going up 1, yeah. And that's important. We can't make this decision until we first decide, are the x's changing by a constant amount? Not a constant ratio. We're not figuring out a constant ratio. Just are they going, is there the same amount of difference between the x's? And there is in this one, they're going up by 1. So then now we check just the y values and we look for that constant ratio. Just like a geometric sequence. So what we're looking for is, are the y values a geometric sequence? So we would do 0 divided by 1. What's that equal? 0. But is that the order I should have done it in? Next term divided by the previous term?
No, it should be negative. Oh, no, never
Doing the y's. So don't we start at, I think the way you guys like to do it, let's look at the way you guys like to do it. You do it like this, 4 divided by 1. You start at the end of the table, don't you? Mm-hmm. End of them. So 4 divided by 1 equals 4. 1 divided by 0 is 1. Oh, can you divide by 0? No, this is undefined actually. And then we have 0 divided by 1, and that equals 0. Okay. So do we have a constant ratio? Do we have a common ratio? No. A constant ratio? No, we don't have a common ratio or a constant ratio. We call it either or. So we would say, is not an exponential function. Is not an exponential function because there is not a constant ratio in y. There's the justification. And we say it is not an exponential function. We did determine that the x's are going up by 1, but then we couldn't find that constant ratio in y. Actually, does anybody think, just looking at that table of values, what it looks like it could possibly be, what kind of function it could possibly be by the behavior of those y's? Remember how just that last function we just studied? Anybody remember the last type of functions we just studied? The u's, what were they? Quadratic? Yeah, the quadratic function. Do you remember what happened to the y values in the quadratic function? Remember how in the table,
Oh, yeah.
the y values would start repeating? So this looks like
Oh, yeah.
this looks like it could be the what? Would that be called the vertex? This
And
looks like it could be the
everything would
vertex.
the same after that.
Yeah, I bet if they extended this table,
-2.
possibly what would the y value be for -2?
4.
4. So this is probably a quadratic function instead of an exponential function. Okay, so just a little sideline there. See if we can,
So that's all we
remember.
have to do then?
Okay, so what we just did for that one, we don't have to do that little sideline I did, but we have to do the rest of it. Okay? Okay, so first thing I said is put them in a table. It actually makes it easier to tell what's happening. Okay? So let's make our table first of all. X, Y, and we have 1, 2, 3, 4 ordered pairs. So what's happening first of all?
X goes up by 1.
So x is going up by 1. X goes up by 1. Always our first thing we check.
Can you just write like X equals plus 1?
Why don't you do this instead? X.
Okay.
Okay. X isn't really equal plus 1, but you don't shortcut it. That would be a way to shortcut it. Okay, and then now we're going to look for our, and remember we don't just check it once, we do it all through the table. So sometimes if you just stop too early, the behavior could change. So we're going to start with our 0.5 and divide it by 1.
0.5.
Well, anything divided by 1 is itself, right? Okay. So there's our first our first constant, our ratio that we checked out. Now we're going to do 1. So we did this term divided by its previous term. Now we do this one divided by its previous term. What is 1/2 as a decimal?
0.5.
0.5.
Hold on, did we miss 0 divided by 1?
No.
No, we're in the y's. We're doing the y's right now. Yeah. The y is what we do the ratio part for. And now we're going to do the 2 divided by the 4. So remember this, we're just doing what we did with geometric sequences. And 2 divided by 4 happens to be 1/2, which also is the same as 0 and 5/10. So do we have an exponential function?
Yes.
Yes, we do. So is an exponential function. And we justify why. We have our work to support it, but what's our reasoning? And is an exponential function, because all of this is going to be important. Because the next thing we're going to do on the back side is we have to write the function. So is an exponential function because as x goes up by 1, the constant ratio for y is 0.5. Is an exponential function because as x goes up by 1, the constant ratio for y is 0.5. So those are justification. Okay? We have to learn how to not only do the work showing what happens, we have to be able to speak it, which we do in words when we speak, and so we have to be able to write those on paper also. So anybody have any question on how we're going to determine if it's an exponential function or not? Okay, now let's go to the back side. Because now what we're going to do is we're going to write the exponential function. So we've decided it is, but now they want us to write the function for it. So writing the exponential function that models the set of ordered pairs, determine A, because remember our model goes like this. Let's put our model up here. Y equals A times B raised to the x power. There's our model. So we need to, have some parts here to sub in. We want an x in our exponential function, we want a y in our exponential function. We want A and we want B replaced. So we have to figure out how are we going to get those A and that A and that B. So determine A. Remember what I said last Friday? A is representing the what?
The first value.
The first value, yeah, the starting point. Where does it start at? Every geometric sequence has to start somewhere, doesn't it? So where does it start at? Well, where it starts at, and we also talked about this on Friday, when we have that starting value, what does x equal? 0. That's when x is equal to 0, because anything raised to the 0 power is, no, 1, and 1 times a would be a. So determine A. What is y? What is y? That's going to be your a value when x equals 0. That's going to be your a right there. What is y when x equals 0? What's your starting value? And the start is when x equals 0. Okay. And then determine b. Well, look at our exponential model right here. B is being raised to a power. Remember what I said on Friday, that b is really representing?
Common ratio.
Yeah, the common ratio, the constant ratio. So common, constant ratio, you can call it either. They both really mean the same thing. Well, we should be able to find both of those things. We just found the constant ratio in one on the front. So then we will substitute into our model then after that, okay? So let's try this first one here. So ordered pairs 0, 4, 1, 12, 2, 36, 3, 108. Okay, so apparently these came from directions that said this is an exponential function, write the model for it. So they're telling us that this set of ordered pair already represents an exponential function. So if it does, then what's our a value, what's our b value, so we can write a model for it. So what's our a value?
0.
Go back up to above when I said, what is y when x equals 0? What is y when x equals 0?
1.
Garcia?
4.
4. Our a value is 4.
Oh.
Our starting value is 4. Look at theirs. If we put these in a table in the order that they are, because the x's are in numerical order, 0, 1, 2, 3, that would be the first value of our table, wouldn't it? It would be the first value of our geometric sequence. Now, be careful though, because you got to be careful about that, because they don't always start the geometric sequence at the a value, okay? So this is the way we want to look at it. Find where x is equal to 0, and that y value will be your a value. Okay, now we need to find b. Well, this has already been told to us that it's an exponential function, so we get to pick any two y values that we can find a ratio between that's legitimate. In other words, we don't want to do 108 divided by 4, but what could we do?
12 and 36.
So which one would be on top, the 12 or the 36?
36.
So think of it, these are the y values. So we have 4, Maybe we should put them in a table, huh? Would that be easier to see? So 36 divided by 12, take a y value, divide by the previous y value. Take a y value, divide by the previous y value. How many 12s are in 36? 3. Let's see if it works for the rest of them, just to make sure this is an exponential function. 12 divided by 4, what's that? 3. What's 108 divided by 36? Will you check it out for us? What's 108 divided by 36? 3. Okay. So our constant ratio is 3. Remember, our constant ratio is our b value. This is how we find our b value. We find the constant ratio. So now let's write down the model. Here's our model. And we're going to sub into our model. The y and the x stay there. We want y and x in there because this model should represent any ordered pair from this exponential function. 4 goes in for A, 3 goes in for B. There's our model. Now, as tempted as you might be, because this is what I already know you want to do, take 4 times 3 and clean this up. And have y equals 12 to the x power.
You take the power.
Yeah, you do the power first. We can't do the power right now because we don't have an x value, do we? So we leave it like this. Now let's just make sure our model actually works. Let's check one of these ordered pairs out and make sure it works. Okay? So in other words, if we put our x value in, do we get the y value that goes when we do it? So let's do when x is equal to 0. 3 to the 0 power, what is that? 3 to the 0 power?
1.
1. Anything to the 0 power is 1. 1 times 4?
4.
4. Our y value should be 4. It is. Let's try it again. When x is equal to 1. 3 to the first power?
3.
3. 3 times 4?
12.
12. We get our y value. Let's do it one more time. 3 to the second power. There's our, we're going x. 3 to the second power is 9. 9 times 4 is 36. It worked, didn't it? Okay. So our exponential model should, when we substitute in the x values from the ordered pairs, we better get the y values that went with those x values in the ordered pairs.
Will we have to show a substitution?
No, no. But that would be a way, especially if you're in a team, you have the right one when you're doing an assessment, and it's worth points, right? Okay, I want you to do this one on your own. I want you to find, see if you can come up with your exponential function for this set of ordered pairs.
Wait, can we choose any one?
You get to pick any of the two y values you want to work with as long as they're side by side. And you take the one to the right and divide it by its one to the left of it. Okay, so you have your exponential function, like you know, have to take you agree, and then we're going to do some reasoning. So See if we have a good answer. Okay, remember what we said last week about constant ratios. If the constant ratio is between 0 and 1, what should be happening to the terms of the sequence as you go on? When the constant ratio is between 0 and 1, or maybe we can start this way. When the constant ratio is greater than 1, what happens to the terms as you go on in the geometric sequence?
It's small.
It's, yeah, small.
They get smaller?
That's how. No, I think it's the other way around.
Let's go see if we have anything we can refer to here that'll.
I think they get.
Okay, let's look at this one. Our constant ratio was 3. We didn't argue that at all, did we? We all were happy with it? And look at what happened to the y values.
They got bigger.
They got bigger.
When it's above 3, it gets bigger. When it's between 0 and 1, I think it's smaller.
Okay, so not when it's above 3, but when it's above
1.
1. When it's greater than 1, then your y values should be growing, shouldn't they? When it's between 0 and 1, they should be getting smaller. Is that what's happening here? Because I ended up with a constant ratio between 0 and 1. Did you? Did you end up with the same constant ratio? Are our y values then supposed to get larger or smaller as we go along? They should be getting smaller. Are they getting smaller? Negative 21? Oh, okay, absolute value of them should get smaller, I better say. So, are their absolute values smaller? The absolute value of negative 20, what is that? 20. Absolute value of negative 5? 5. Is 5 smaller than 20?
Yes.
Yes. So, we don't want to just write exponential functions and say, well, good enough. We're going to have exponential functions that make sense to the situation. And how do they become negatives? Because our a value is negative, isn't it? So a negative times a positive will be a negative times a positive will always be a negative. So we want to make sense of our exponential functions also. So the reason that we wrote our constant ratio as a decimal is because the a value was a decimal. Typically, you'll see those kind of correspond. If the a value had been a fraction, then we would probably leave our constant ratio as a fraction too. Okay? Any questions?